Hello, this is Priyanka Srinaskar again coming with the next part of our last video. Let us discuss the sums of physics of class 10 ICSC from number 10 to the rest. At first, let me start with the number 10 sum. Here it is a diagram. This diagram shows a uniform bar supported at middle point O. This is the support, middle point O. A weight of 40 GF. A weight of 40 GF is placed at a distance of 40 centimeter. This is 40 centimeter to the left from the point O. Now we have to find that at which distance we have to place the weight of 80 GF to balance the bar. Okay. So our F1 is 40 GF and D1 is, we know, 40 centimeter. F2 is given here 80 GF. We have to find out the D2. According to the formula, F1 D1 equals to F2 D2. Simply put the values. F1 equals to 40, D1 is equals to also 40, F2 is equals to 80. We have to find the unknown D2 here. So D2 becomes 40 into 40 by 80. Now make the calculation. That is D2 equals to, we got 20. That means we have to place the 80 GF weight at 20 centimeter to the right of O. Let us come to the number 11 sum now. Here is a figure on the next page which shows a uniform meter rule placed on a fulcrum at its midpoint O having a weight 40 GF at the 10 centimeter mark and a weight of 20 GF at the 90 centimeter mark. Fine. Let us draw the diagram first. This is our meter rule. Let me draw the diagram first. This is the fulcrum placed at O. So a weight of 40 GF is placed at the 10 centimeter mark. The fulcrum is at the midpoint, that is on the 50 centimeter mark, and a weight of 20 GF is placed at the 90 centimeter mark. Okay. First we have to find that whether the meter rule is in equilibrium or not. From here we got F1 equals to 40 GF. D1 equals to 50 minus 10. That means 40 centimeter from the midpoint. F2 is 20 GF and D2 is 90 minus 50. That is 40 centimeter from the midpoint. Now find out F1 D1, which is 40 into 40, that is 1600, and F2 D2, which is 20 into 40, that is 800. Now from these two calculation we can find out that F1 D1 is greater than F2 D2. Therefore the bar is not in equilibrium, and since F1 D1 is greater, therefore the movement will be around this side, that means anti-clockwise. Therefore the answer of the first part will be the meter rule or the bar is not in equilibrium and the movement will be along anti-clockwise. Okay. Now there is a second part also. How can the rule be brought in equilibrium by using an additional weight of 40 GF? Okay. We can see from this calculation that F2 D2 is lesser than F1 D1. So you have to place the 40 GF weight in the side of F2 D2. Okay. So let place the weight 40 GF at X centimeter from midpoint. So we have to add the weight momentum with the second one, that is with the 800 GF. So 800 plus 40 into X, and these will be balanced with the first momentum, that is 1600. From this equation we have to find out the value of X. We can find that X equals to 20 centimeter. Therefore we have to place the weight of 40 GF at 50 plus 20, that is 70 centimeter mark. Let us move on the next sum, that is number 12. When a boy weighing 20 kgf sit at one end of a 4-meter long seesaw, it gets depressed at this end. How can it be brought to the horizontal position by a man weighing 40 kgf? Okay, let us draw the diagram first. This is our seesaw of 4 meter. Fine. This is the midpoint. That means this one is 2 meter. And the boy is here. Weight of boy is 20 kgf. That means F1 equals to 20 kgf and D1 equals to 2 meter. And a man of 40 kgf will sit here to balance the seesaw. So F2 equals to 40 kgf. We have to find the D2. That is, we have to find this distance. We know the formula F1 D1 equals to F2 D2. That is 20 into 2 equals to 40 into D2. From here we got 40 by 2, sorry, 20 into 2 by 40 equals to d2. That means we have got d2 equals to 1. That means the man has to sit 1 meter from the midpoint opposite to the boy's direction. Now, number 13 sum. A physical balance has its arms of length 60 centimeter and 40 centimeter. So this is our physical balance. This arm is of 60 centimeter and this arm is of 40 centimeter. Fine. What weight kept on the pan of longer arm will balance an object of weight 100 gf kept on the other pan? That means a weight of 100 gf is placed at the 40 centimeter arm. We have to find which weight must be put on the longer arm to balance the for the equilibrium position. So F1, we have to find out F1. D1 we know 60 centimeter. F2 is given 100 gf and D2 is also given the shorter arm, that is 40 centimeter. The formula says that F1 D1 equals to F2 D2. F1 is unknown to us. We know the value of D1 is 60, F2 is 100 and D2 is 40. From this equation we have got the value of F1. F1 equals to 200 by 3, or if we convert this into decimal, we will get the value that 66.67 GF approx. So this is the result of number 13 sum. Okay, now 14 sum. It's a quite big sum but easy. Here is a diagram which shows a uniform meter rule of weight 100 gf. Pivoted at its center O. Two ways of 150 gf and 250 gf is hang from the points A and B of the meter rule. OA, the distance OA is 40 centimeter and OB is 20 centimeter. In the number 1 part, we have to find the total anti-clockwise moment about O. Okay. At the point A, the weight is 150 gf. That means this will turn this way, and this one is the anti-clockwise moment. So we have to find the moment at O at the first part. Here F is 150 and the distance is 40. So the anti-clockwise moment will be this, 6000 gram force centimeter. Now number 2 part. The difference of the In the number 2 part, there is total clockwise movement. Total clockwise movement. About O. At the point B, the moment will be at the direction this. That means clockwise. So we have to find out the moment at B to find out the clockwise moment. Here F is 250 and D is 20. So the clockwise moment will be 5000 gram per centimeter. Now the number 3 part. We have to find the difference of anti-clockwise and clockwise movement. So the difference will be 6000 minus 5000, that is 1000 gram per centimeter. Here is another one part, that is number 4 part. The distance from O where 100 GF weight should be placed to balance the meter rule. From these two calculations we can see that anti-clockwise moment is greater than clockwise moment. So we have to place the 100 GF weight at the site of clockwise moment to balance the meter rule. So let 100 GF weight should be placed at X centimeter from O. We have to add the moment with the clockwise moment to balance the anti-clockwise moment. So from this equation we have to find the value of X. That is X equals to 10. So we have to place the 100 GF weight at 10 centimeter from O at right side, that is at the direction of clockwise moment, at the right side. Number 15 sum. A uniform meter rule of weight 10 GF is pivoted at its 0 mark. Let us draw the diagram first. Pivoted at 0 mark and a weight of 10 GF is suspended from here. This is the midpoint and this is the end point. F1 equals to 10 GF, D1 equals to, we have to find the distance from the midpoint, that is 50 minus 0, so 50 centimeter. So moment will be F1 D1, that means 10 into 50, that is 500 gram per centimeter. Now the second part. How can it be made horizontal by applying a least force? Okay, so we have to apply a force of F2. So let the force be F2 GF. D2 will be 100 centimeter since the rule is pivoted at the 0 mark, so D2 will be 100 centimeter. To make the rule horizontal, F1 D1 must be equal to F2 D2. And we know the value of F1 D1 500 GF from the previous part. We have to find out F2 and D2 is 100. So we got F2 equals to 5 GF. So we have to place weight of 5 GF to balance the meter rule. Number 16 sum. A uniform half meter rule can be balanced at the 29 centimeter mark when a mass of 20 gram is hung from its one end. Okay, this is a half meter rule. That means total length is 50 centimeter. So midpoint will be definitely 25 centimeter and a mass of 20 gram is hung from its one end. So we have to find out the mass of the half meter rule. We have to find F1. D1 is given, that is 29 minus 25, that is 4 centimeter. F2 we know 20 gram and D2 50 minus 29. Since we have to balance the meter rule at the point of 20 centimeter mark, so D2 will be 50 minus 29, that is 21 centimeter. So from the formula F1 D1 equals to F2 D2, we have to place the values of the known, that is D1, F2 and D2. We will get the value of F1. F1 equals to 100 gram. So we have to place a weight of 105 gram to balance the meter rule. Number 16 sum. A uniform half meter rule can be balanced at the 29 centimeter mark when a mass of 20 gram is hung from its one end. Okay, this is a half meter rule. That means total length is 50 centimeter. So midpoint will be definitely 25 centimeter and a mass of 20 gram is hung from its one end. So we have to find out the mass of the half meter rule. We have to find F1. D1 is given, that is 29 minus 25, that is 4 centimeter. F2 we know 20 gram and D2 50 minus 29. Since we have to balance the meter rule at the point of 20 centimeter mark, so D2 will be 50 minus 29, that is 21 centimeter. So from the formula F1 D1 equals to F2 D2, we have to place the values of the known, that is D1, F2 and D2. We will get the value of F1. F1 equals to 100 gram. So we have to place a weight of 105 gram to balance the meter rule. Number 17 sum. A uniform meter rule of mass 100 gram is balanced on a fulcrum at the mark 40 centimeter by suspending an unknown mass M at the mark 20 centimeter. Fine. Let us draw the diagram first. This is our meter rule. This is the fulcrum at 40 centimeter mark. This one is the midpoint, that is 50, and the mass M is suspended at the 20 centimeter mark. we have to find the value of m. So F1 is m, D1 is 20 centimeter. We have no F2 100 gram and D2 equals to 10. So F1 D1 equals to F2 D2. M into 20 equals to 100 into 10. M equals to 100 into 10 by 20. So M equals to 50 gram. This one is the first part. To which side of the roll will tilt if mass M is moved to the mark 10 centimeter? If we move the mass M to the mark 10 centimeter, in which direction the roll will move? Let this be the 10 centimeter mark. If we move the mass M to this one, so the movement will be along this side, that is anti-clockwise. Now the third part. What is the resultant moment now? F1 D1 equals to F1, we know the value of F1 now, which is M, that is 50, and D1 will be 40 minus 10. Since the fulcrum is at 40 and we have moved the M at the 10 centimeter mark, so D1 will be 40 minus 10. This is F1 D1 and thus this direction is anti-clockwise. Now for F2 D2, F2 is 100 and D2 will be 50 minus 40. Since the midpoint is at 50 and fulcrum is at 40, so the D2 will be 50 minus 40. That is the moment F2 D2 will be 1000 gram per centimeter, and this direction will be clockwise. So resultant moment. Clearly F1 D1 is greater than F2 D2, so the resultant moment will be 1500 minus 1000, that is 500 gram force, and the direction will be anti-clockwise. In the anti-clockwise, moment is greater. Here is another part of this sum. How can it be balanced by another mass of 50 gram? So clearly F1 D1 is greater than F2 D2. So we have to place the mass of 50 gram at the side of F2 D2, that is clockwise. Let the 50 gram mass should be placed at X centimeter. The clockwise moment was 1000. We have to add this to balance this one with 1500. We have to find out X from this equation. So x equals to 10. So the mass should be placed at 40 plus 10. Since the fulcrum is at 40 centimeter mark, so we have to place the mark at 40 plus 10, that is at 50 centimeter mark. Now the last sum, number 18. A uniform bar of length L meter is supported at its end and loaded by weight W kgf at its middle. In equilibrium, find the reactions R1 and R2 at the ends. Let us draw the diagram first. This is our bar, which is of length L meter. W is in the middle, and these are two reactions, R1 and R2 respectively. Since W is in the middle, clearly this distance is L by 2 and this distance is also L by 2. So from this diagram we got F1 equals to R1 and D1 equals to L by 2 and F2 equals to R2 and D2 equals to also L by 2. The formula is F1 D1 equals to F2 D2. If we place the values, R1 into L by 2 equals to R2 into L by 2. From this, clearly we got R1 equals to R2. Now since these two reaction forces balance the W, so R1 plus R2 is equals to W for equilibrium position. Now if we replace R2 by R1, from the number 1 equation, we got 2R1 equals to W, that is R1 equals to W by 2. And since R1 equals to R2, therefore we got R2 equals to also W by 2. So we got the value of R1 and R2 both W by 2 kgf. So this is the end of this chapter. I will again solve the numericals of the next chapters very soon. Do subscribe my channel and don't forget to click on the bell icon. Thank you so much. Goodbye.